Matter in our surroundings. Matter is anything that has some mass and occupies some volume. Matter is made up of small tiny particles. Particles of matter are continuously moving. The matter around us can exist in three states: solids, liquids, and gases. A solid state is a state in which matter is characterized by having definite shape, distinct boundaries, rigidity, incompressibility, and fixed volume. A liquid state is a state in which matter is characterized by having fluidity, low compressibility, no definite boundary or shape, but has fixed volume. A gaseous state is a state in which matter is characterized by having fluidity, high compressibility, no definite boundary, volume or shape. The forces of attraction between the particles are maximum in solids, intermediate in liquids, and minimum in gases. The state in between the constituent particles and kinetic energy of the particles are minimum in the case of solids, intermediate in liquids, and maximum in gases. The arrangement of particles is most ordered in the case of solids. In the case of liquids, layers of particles can slip and slide over each other, while for gases, there is no order. Particles move about randomly. The state of matter are interconvertible. The state of matter can be changed by changing temperature or pressure. SI unit of temperature is Kelvin. Temperature of Kelvin is equal to temperature in Celsius degree plus 273. The temperature at which solid melts to form liquid at atmospheric pressure is called melting point. The temperature at which a liquid starts boiling at the atmospheric pressure is known as boiling point. Sublimation is the change of solid state directly to gaseous state without going through liquid state. Deposition is the change of gaseous state directly to solid state without going through liquid state. Boiling is a bulk phenomenon. Particles from the bulk of the liquid change into vapor state. Evaporation is a surface phenomenon. Particles from the surface gain enough energy to overcome the forces of attraction present in the liquid and change into the vapor state. The rate of evaporation depends upon the surface area exposed to the atmosphere, temperature, the humidity, and the wind speed. Evaporation causes cooling. Latent heat of fusion is the amount of heat energy required to change 1 kg of solid into liquid at its melting point. Latent heat of vaporization is the amount of heat energy required to change 1 kg of liquid into gas at its boiling point. Interconversion of three states of matter. Some measurable quantities and their units. Temperature, Kelvin, K. Length meter m, mass kilogram kg, weight Newton N, volume cubic meter m cube, density kilogram per meter cube, kg per m cube, pressure Pascal PA. Melting point of ice is equal to 0 degrees Celsius or 273 K. Boiling point of water is equal to 100 degrees Celsius or 373 K. Latent heat of fusion of ice is equal to 80 calories per gram. Latent heat of vaporization of water is equal to 540 calories per gram. Activity Aim: to observe the effect of dissolving salt or sugar in water on the water level. Apparatus used: 100 ml beaker, water, salt or sugar, glass rod, marker pen, measuring cylinder. Procedure: take a clean and dry 100 ml beaker and fill it up to half its volume with water. Mark the level of water in the beaker with a marker pen. Using a glass rod, dissolve a small amount of salt or sugar in the water. Observe any changes in the water level. If the water level has changed, measure the volume of water with a measuring cylinder. Observations: on dissolving salt or sugar in the water level may change. The level of water may increase or decrease depending on the amount of salt or sugar added. If the water level has changed, measure the volume of water with a measuring cylinder. Sometimes the salt or sugar may disappear and dissolve completely in the water. Conclusion: the experiment demonstrates the effect of dissolving salt or sugar in water on the water level. Depending on the amount of salt or sugar added, the water level may increase or decrease. In some cases, the salt or sugar may dissolve completely and disappear in the water. The experiment helps in understanding the properties of solutions and the changes they can cause in the volume of the solvent. Activity Aim: to observe the effect of dilution on the color of a solvent. Apparatus required: potassium permanganate crystals, water, 100 ml measuring cylinder, 5 beakers or test tubes, glass rod or stirring rod. Procedure: take 2 to 3 crystals of potassium permanganate and dissolve them in 100 ml of water. Take out approximately 10 ml of this solution and put it into 90 ml of clear water in a beaker or test tube. Stir the solution with a glass rod or stirring rod. Take out 10 ml of this diluted solution and put it into another 90 ml of clear water in a different beaker or test tube. Repeat the process of dilution with the new solution in a fresh beaker or test tube 5 to 8 times. Observe the color of the solution after each dilution. Observations. The initial solution of potassium permanganate is deep purple in color. As the solution is diluted with clear water, the color becomes lighter and lighter with each dilution. After 5 to 8 dilutions, the color of the solution becomes almost colorless. Conclusion. The experiment demonstrates the effect of dilution on the color of a solution. As the solution is diluted with clear water, the water becomes lighter and lighter with each dilution until it becomes almost colorless. This experiment helps in understanding the properties of solutions and the effect of dilution on their concentration. Activity Aim. To observe the effect of diffusion of gases on the spread of odor. Apparatus required. Unlit incense stick, matchbox or lighter. Procedure. Put an unlit incense stick in a corner of your classroom. Walk towards the incense stick from a distance and observe how close you have to go to smell it. Light the incense stick with a matchbox or lighter. Observe how the smell of the incense stick spreads in the classroom. Walk around the classroom and observe at what distance you can smell the incense stick. Observations. Before lighting the incense stick, one may have to go near it to smell it. After lighting the incense stick, the smell spreads rapidly throughout the classroom. The smell of the incense stick can be sensed from a greater distance after it is lit. Conclusion. The activity demonstrates the effect of diffusion of gases on the spread of odor. Before lighting the incense stick, the odor is restricted to a small area around it. But after it is lit, the odor diffuses rapidly and spreads throughout the classroom. This activity helps in understanding the process of diffusion of gases and how it affects the spread of odor. Activity Aim. To observe the process of diffusion in liquids. Apparatus required. 2 glasses or beakers. Water. Blue or red ink. Honey. Procedure. Take 2 glasses or beakers filled with water. Put a drop of blue or red ink slowly and carefully along the sides of the first beaker Honey in the same way in the second beaker. Leave them undisturbed in your house or in a corner of the class. Record your observations. Observe immediately after adding the ink drop and record your observations. Observe immediately after adding a drop of honey and record your observations. Observe and record how many hours or days it takes for the color of ink to spread evenly throughout the water. Observations. Immediately after adding the ink drop, we can observe that the ink begins to spread in the water. Immediately after adding a drop of honey, we can observe that the honey remains in a drop form and does not mix with the water. It may take several hours or even a day for the color of the ink to spread evenly throughout the water. Conclusion. The experiment demonstrates the process of diffusion in liquids. Diffusion is the process by which the molecules move from an area of high concentration to an area of low concentration. When a drop of ink is added to water, the ink molecules spread out and mix with the water molecules until they are evenly distributed. Honey, on the other hand, is a non-polar substance and does not mix with water molecules. This experiment helps to understand the properties of liquids and the process of diffusion. Activity. Aim. To observe the rate of mixing of a solid crystal in a hot and cold water. Apparatus required. Copper sulfate or potassium permanganate crystals. Hot water, cold water. 2 glasses or beakers. Stirring rod. This is optional. Procedure. Fill 2 glasses or beakers, one with hot water and the other with cold water. Drop a crystal of copper sulfate or potassium permanganate into each glass. Observe the crystal just above the bottom of the glass. Do not stir the solution and allow the crystal to settle. Observe what happens as time passes. Note the rate of mixing of the crystal in each glass. Repeat the experiment with different solids or temperatures if desired. Observations. Just above the solid crystal in the glass, a clear boundary is visible where the water appears to be separate from the solid. As time passes, the crystal gradually dissolves and mixes with the water. The rate of mixing is faster in the hot water than in the cold water. This suggests that the particles of the solid crystal have more energy in hot water and therefore move faster and mix more quickly with the water. Conclusion. The experiment demonstrates that the rate of mixing of a solid crystal in water is affected by the temperature of the water. The particles of the solid crystal have more energy in hot water, which results in faster mixing with the water. This experiment helps in understanding the properties of solids, liquids, and their interaction. Note: it is important to handle chemicals with care and follow safety precautions while performing this experiment. Activity. Aim. To compare the strength of the particles holding together iron nail, chalk and rubber band. Apparatus required: an iron nail, a piece of chalk, a rubber band, hammer, scissors. Procedure: take the iron nail, chalk and rubber band separately. Try breaking the iron nail by hammering it. Try breaking the chalk with cutting it with scissors. Try breaking the rubber band by stretching it. Observe the results of all three attempts. Based on your observations, decide in which of the three substances the particles are held together with great force. Observations and conclusion: the iron nail could not be broken by hammering, indicating that the particles holding it together are held together with the greatest force. The chalk could be easily broken by cutting, suggesting that the particles holding it together are not held as tight as in the iron nail. The rubber band could be easily broken by stretching, indicating that the particles holding it together are not held as tight as in the iron nail. Therefore, it can be concluded that the particles holding together the iron nail are held together with the greatest force among the given substances.